Be in prayer. Heavenly Father, we thank you for this day. Again, Lord, thank you for these students. Pray for all the students who couldn't be here today, that they would feel better soon. And we thank you, Lord, for all your many blessings to us this day, Lord. In your name I pray. Amen. So, yeah, we're going to talk about existence and uniqueness theory for differential equations. And so this is chapter 13 in Nagel, Saff, and Snider's differential equations book, which I happen to have the 5th edition of here. So I cut out the 13th chapter. And if you start looking at this, what he does is he starts by
I'm going to take this and drop it.
Okay. Let's just start. Let's kind of try to follow him along here. These first initial thoughts, and then we'll skip to section 2 here before too long. So basically the problem is we're studying something like how do you solve the initial value problem. Y prime as a function of x, of course, is equal to some given function of x and y of x, all right? So you might, in other notation, you might say we're trying to solve dy dx is equal to f of xy, right? And we're also given that y of x naught, we're given this initial data piece, y of x naught is equal to y naught, all right? What we're going to see today is that we can use the contraction mapping technique in order to understand the existence and uniqueness theorems for ODEs. That's where we're going. And the proofs in here you'll find are accessible and actually pretty easy to understand, and weirdly and strongly related to the things we did. I mean, we were looking at inverse function theorem last time, right? Now I'm talking about solving differential equations, but you'll see that the arguments are strikingly similar. Now, so the first thing he does here is he just integrates from x naught to x, right? Y prime of t is a dummy variable integration, of course, y prime of t dt. Well, fundamental theorem of calculus says that that's y of x, right? Minus y of x naught. On the other hand, because we're solving that differential equation, it's also the integral from x naught to x of what? F of t comma y of t dt. Right. So continuing on here, what's that give us? We have, well, what we have then is we've got y of x is equal to y naught plus the integral from x naught to x, of course, of f of t comma y of t dt. Right. Right. In other words, what he's doing is simply this. He's recasting this initial value problem, this differential equation paired with an initial condition, aka initial value problem, right? IVP, initial value problem. And he showed that that is in fact equivalent to this integral equation, right? And you see why it's called an integral equation. I think that's fairly obvious. Okay, so we've traded a derivative for an integral. And so what does he say here? He said, conversely, using the fundamental theorem of calculus, if f and y are continuous, then a solution of the integral equation must be a solution to the initial value problem. So these are interchangeable. And then here is where it starts to get interesting. He's like, so equation 4, the integral equation naturally yields itself to an operator interpretation. Right? So in particular, you could think of this differential equation as being this operator t of y, right, equals to what? You know, y naught plus the integral. Well, excuse me, I'm still not saying this right. This is the value of the function at x, right? So to be careful, I should say this operator is defined point-wise as follows. So t of y is a function, its value at x is y of x, right? in particular, it's the integral. In particular, it's y naught plus the integral from x naught to x f of t comma y of t dt. Well, so all right, just let me just try to take the abstraction out of this just a little bit for a second here. So suppose we have, for example, y prime equals to x times y. All right. Then, and let's say y of times 0 is equal to 1, right? Then what's t of y? One, right? Plus the integral from 0 to x of, let's see here, t. How's it go? So this is my f of x comma y, right?
It's going to be ty of t.
So t y of t, you say? dt, right? I mean, this y is a function. It's really y of t, right? Okay, let's try. So take this operator, right? And feed it e to the x. What happens? I mean, I guess maybe I should say feed it e to the t, if you like. I could say feed it y, such that y of t is equal to e to the t. That would cause me the least pain, but the most writing. Okay, and then what happens? Well, you got 1 plus the integral from 0 to x of what? T, oh, why did I do this? E to the t dt. I guess I can do that in my head. 1 plus e to the t times what? 1 plus t, the value from 0 to x. Right? So we get 1 plus e to the x times 1 plus x minus e to the x, I think.
Wait, did you integrate or differentiate?
Oh, it's a good question. If I differentiate that, I reckon I better put a minus 1 here, huh? E's correct? Which makes it a plus.
Yeah.
Because if I differentiate this,
Right. Okay.
I get e to the t plus t e to the t,
And then
and
minus
then
e to the t.
minus e to the t from the, yeah, okay. You're right, I was differentiating. Okay. Okay, so the e to the x is cancel. What do you got? 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 1 plus x e to the x, right? Right. By the way, of course, this is not equal to y of x,
Yeah. Doesn't make sense, so that's not a solution.
which means that y, the given y, is not a solution. Now, if we were to solve this and feed a solution to it, then if you believe the derivation we just went through, you'd get back y again. So I guess I'll leave that as an exercise to the watcher to actually solve this. I mean, I'll solve it.
Yeah, it's not just your
Yeah,
separation.
but you get dy over y is equal to x dx, yeah. So you got like natural log, that's why y is equal to 1/2 x squared. So you have something like y is equal to like k e to the 1/2 x squared, something like that, right? But, yeah, whatever. Okay, fine, I guess it's a u substitution, blah, 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 blah. It's not too bad, but there you go. So the point is, now we have traded the differential equation, the initial value problem, for the sort of equivalent problem of looking for fixed points of a particular operator. So t of y equals to y if and only if y solves the initial value problem, right? It's pretty cool. And I guess this is, as much as this is reminiscent of linear algebra, you should be careful not to get too carried away. I mean, this t doesn't even have to be linear, right? Like the y can appear here with a square or something, right? So this is not even a linear operator, it's just an operator on functions. So then the remainder of this section, he then talks about Newton's law, he talks about Newton's equation, he talks about Newton's method, like we talked about before, and he mentions this method of successive substitutions to find roots, like we talked about, and he gives Banach's fixed point theorem, theorem 1, and you notice, this is a very pragmatic text. He doesn't characterize it in terms of a contraction mapping. He's like, suppose g is a differentiable function on a closed interval I, and g of x lies in I for all x and I. If there exists a constant such that the absolute value of g prime of x is less than k was less than 1, then the successive operation, successive approximations defined by xn plus 1 equals to g of xn converges to this solution. For any, you can solve x equals to g of x by iterating xn plus 1 equal to g of xn. But you notice the way he characterized it is the way actually we did in our applications last time, right? We didn't actually, what we did was we showed the derivative is bounded, and we used that to imply the existence of the contraction mapping constant. You just get straight to the point. It's like, just suppose the derivative is bounded. Well, the bound is the contraction mapping constant, right? So that's pretty cool. Now there's something else here that's a new idea and is an important idea. One of the things he mentions in this section 1, is he's like, so again, we're trying to think about how do you solve like x is equal to g of x, just as a, this is not our goal, it's just it's a waypoint on the way to what we're talking about, but you're trying to solve this equation essentially. You're looking for a fixed point of this. So so you start out somewhere. You start out with x naught in the domain of g, right? And he says you let x1 equal to g of x naught, right? And we're assuming what? We're assuming, as I mentioned a second ago, the absolute value of g prime of x is less than k for all x in the interval of consideration, right? And here g is a real valued function of a real variable. The new idea, and maybe this is special to our particular application here, is that you can look at the iterate, right, xn, as equal to, and this is kind of sneaky, it's x naught plus x1, right, minus x naught plus x2 minus x1 plus plus xn minus xn minus 1. Let's see if I can write this. In other words, the xn is equal to x naught plus the sum j equals 0 to infinity of, well, that's not quite it. I'll get to it in a second here. Just, this is not, wrong. X naught plus the sum x. Just a second, let me use my words. So you have this infinite series, right? If this is the infinite series, the nth partial sum of this, xn, is nth partial sum, right? That's really nice because if we're analyzing the convergence of xn, we can use what we know about infinite series to judge the convergence of the iterate. That's a new idea. We weren't doing that last time at all. And that plays a significant role in his thinking in the future sections of this chapter as well. So that's something that it's worth sort of pointing out now. Anyway, so then he goes through and he proves. Tempted to go through this, but I'm going to go on. All right. So I would encourage you to read that if you want to understand what we did before, again, from a different perspective. I probably should go through it, but if you guys want me to go through it, I can go through it. Okay. So that brings us to section 13.2, which is basically how to say this? It's building off this idea, but so you notice that this whole discussion here about Newton's method, right? We're solving a function. G is a function from R to R, right? The input's a number, the output's a number. We're solving an equation. What's the answer? Answer ultimately is a number, right? When you're up here, it's a different context. Here, we're plugging in a function, we're getting out a function. This is a function of functions. Some people would call it a functional. Other people would call it an operator. An operator takes in a function and gives you back another function. So in order to understand the corresponding arguments to these ones that I skipped over just now, we have to understand how do you understand the convergence and so, I mean, how do you understand convergence and so forth in the context of operators? So instead of asking the question, how close are 2 points, we have to ask the question, how close are 2 functions? All right, and so let's talk about that. I think this chapter is exceedingly clear on how to think about that. I'm very, very excited about this. So we're going to consider functions on some closed interval a to b, okay? And the first question we ask is, what do we mean if we have a sequence of functions y sub n, right? If you have a sequence of functions y sub n, so here y sub n is like a function, right, from a to b to the reals, whatever, for each n. Suppose you have a sequence of functions, right? And it converges to a function, this converges to a function y. What does that mean? How should we understand that? It's like intuitively we want the functions yn to get close to the function y as n approaches infinity. Okay, fair enough. But what do we mean by the word close, right? How do you judge how close 2 functions are? And well, first of all, we're going to say that this mumbo jumbo up here means yn is an element of C, A, B. This is going to be the continuous functions with domain A to B. Continuous, yeah, we're just assuming continuity at the moment. So here's the deal. The norm of y, so if y is an element of the continuous function from A to B, we define the norm of y as follows. Use double bars. Y, it's going to be the max x in the closed interval from A to B of the absolute value of y of x. Now we did talk about this idea in Edwards, right? Mm-hmm. We used the
zero norm?
Yeah, we used the zero norm, but there we were thinking about something a little bit more general. This is a little bit more specialized than that, so I think it's going to make more sense to you guys too. So like in Edwards, we were looking at functions to and from, I think, a vector. Like we were looking at functions from Rn to Rn or Rn to Rm or something like that. So we wouldn't judge the distance in the target space of the function. It was itself a vector, so we had to talk about how you judge the length of the vector, and I think we used the zero norm for the length of the vector there, and then we used the max of the zero norms to define the length of the operator. But this is, I suppose, a specialization of that in some sense. I mean, it's not the same, I guess, because that's not the zero norm. That's just absolute value. What's the zero norm? Was it?
It's the max of the absolute values, I think.
Oh, maybe this is. okay, then this is the same. This is just that, and n equals 1 then.
Instead of like with a vector, it's just for each x.
Right.
Instead of the components of the vector, it's for each x.
For each x. Yeah, well the thing is both the domain and the range are one-dimensional. If I had been a better instructor, I would have showed you guys this one first, and then put Edwards upon you. That would have been smarter, right? I'll have to rearrange the order of the videos in the playlist. But then we'll have all these comments about Edwards and be like, woo. It's not like anyone's watching, it's okay. Except for Jess. See her. Excuse me. Where are we? So that's the norm. And like he says, you could call it, I mean, if you wanted to, you could, if you called this interval, if you call this thing I, then you might call this the norm with respect to I. I mean that, if it's important.
PM.
Shut up. Oh, it's messing with us. You might adorn it with a sub I just to emphasize that. All right. So likewise, if you have two functions, right, then the distance between those will just be the norm of the difference, right? And if you think about that, if you were to look at a graph of y and a graph of z, and you could do that here because they're functions, it would just be relative from a to b, like what's their maximum separation between the graphs. That would be their norm. And you can show that in fact it is a norm, right? It has the usual properties of norm, like it's, if you have the norm of y minus z is equal to 0, that tells you that y is equal to z, right? And that's if and only if. And if you have the norm of, like the length of cy is equal to the absolute value of c times the length of y, that makes sense. And it's got triangle inequality. These are all pretty easy to prove. Even the last one, because if you think about it, the max of this, so like in principle the max of this could have some kind of cancellation, right? But this won't, so it's got to be bigger. I don't know, I'm being somewhat sloppy there, but you can prove it. All right, so this gives us the notion of uniform convergence. What's uniform convergence? We say yn, and he uses some kind of special notation, I've never seen this anywhere else, but it's not bad. Yn uniformly converges. I suppose we could use one of our various special arrows, like, it should be like a thick arrow, or something.
An arrow with a loop through.
An arrow with a what?
With a loop-de-loop or something.
A loopy. Well, I'll stop. The y, if the limit as n goes to infinity of the norm of yn minus y is equal to 0. And so what that means graphically is something like this. If we're looking, if this is A and this is B, whatever, and oh no.
Isn't it beautiful?
Sorry, Jess.
That's what you always dreamed of.
You can blame, I don't know.
You can blame me, it's okay.
Blame Nathan? I was going to say blame Oprah. Whatever. So, suppose this is the graph of y, right? Then perhaps the graph of y sub naught might look like, who knows, I mean the graph of y naught could begin at all kinds of crazy junk. Y naught could be like this, I don't know. Right? But the point is, if you thank you. Very good. One more semester. One more semester. Several more weeks. Three more. Chill. Relax. It's okay. All right. stop talking to myself. So if you pick any epsilon you like, right, that would correspond to some sort of, so this guy is the y, right? So an epsilon band would be something like this. You can imagine, you can kind of envision like this epsilon ribbon, plus or minus epsilon ribbon. And the point is you can choose n sufficiently large so that all of the sequence functions, right, you know, they're all, you know, whatever they look like. My picture's about to get very busy, but the point is, past some, maybe this is like y, this blue one maybe is y sub 10 or something, right? And for this epsilon past 10, like 11 to infinity, they're within the thing. And so that's uniform convergence. If you can pick, the thing is you can squeeze into the limit function with one big N, right? For all points. In contrast, of course, you can talk about pointwise convergence, right? What's the difference with pointwise convergence? You could just say yn converges to y if the limit as n goes to infinity of yn of x is equal to y of x for all x in AB, right? And so there it might be to get epsilon within 0.1 at, say, x equals to a, maybe you could use a capital N of 100, but to get to within epsilon of 0.1 at b, maybe you need to use a capital N of 1,000. So you can have different, you know, the way it converges can be different at different points, and that's not a uniform convergence. There's not a universal n that will work across the whole thing. I mean, that notion of universal n is built into this because it's, of course, you know, maximum on the whole interval. That makes sense? So, but on the other hand, of course, if you have uniform convergence, right, if this is going to 0 as n goes to infinity, because the norm is continuous, that also implies that yn minus y is going to 0.
Forgot to staple the graph.
That's okay. I'll take it. Thank you. Okay, so again, uniform convergence implies pointwise convergence, but it's well known that the converse is not the case, right? Have I talked to you guys about this before? I talked about it some in advanced, or no?
I think we did in complex.
It was in complex. Have I talked to you about it before, Nathan?
I mean, I'm familiar with it. I don't.
You don't know from where?
Yeah.
Okay, so like here's the,
I mean, I think we actually talked about it in calculus too, if not by that name.
Ah.
But yeah, I don't know. Probably covered it in. I think we covered it in advance, didn't we? Like that first week from the
I don't remember what I can't remember everything I did in advance at the moment, so it's hard for me.
I feel like we went over it like close to the beginning.
Okay, well, I mean the central result is that, I mean there are many central results. One of the results is that if you have a uniformly convergent sequence of continuous functions, the limit function is likewise continuous. However, if you have a pointwise, if you have something that converges pointwise, then the limit function doesn't have to be continuous. For example, there's counterexamples to that. Standard one being, like, you look at 0 to 1, and you let yn of x equal to x to the n. Oh, just x to the n, right? Yeah. So like that. Of course, x to the n is continuous on 0 to 1, but let's say n equals 1. So yeah, like this guy, right? Then you got this guy, then you got this guy, then you got this guy, then you got this guy. Well, you get the idea. So eventually, the limit function, what it actually converges to pointwise, Point-wise, it converges to this thing, right? It just jumps up here. So of course the limit function is not continuous at 1, and yet all of the sequences, the functions in the sequence are continuous, so disturbulating. And then if you want to get differentiability of the limit function, it requires extra hypotheses. It's anyway. We don't need to develop the whole theory of uniform convergence today. I'm just trying to give you a flavor. All right, so then what? We've got an example here. We will skip it. All right, so this is in the previous section. We proved under suitable conditions the sequence of approximations obtained by the method of successive substitutions converged to a fixed point of the function. This was a consequence of the Banach fixed point theorem for functions on a closed interval I. To prove the Picard iterations converge, by the way, this right here, so the Picard iteration would be what? It would be T y n equals to yn plus 1, right? So you'd start with y of x naught equals to y naught. So that's like the, I think you start with a constant function, that, and then start iterating. That's the Picard iteration. It's the differential equations analog of Newton's method. It's actually really fun to do this for specific examples. I have assigned problems in the past in differential equations for this. Maybe once, really. Maybe the last time I taught it, I got to this. All right. Unfortunately, differential equations has become so tainted with applications, it's hard to fit math in lately. You're not supposed to say these things. You know, it's not. It's a beautiful applied course. Let's see here. Actually, there's really nice math in differential equations if you're allowed to talk about it. So where are we? I'll get to it. So that brings us to the analog of the contraction mapping theorem for operators. That's what we want to prove and understand. That's our next move here. All right, so. Here it is. So we're going to look at the theorem for operators defined on the closed interval. Basically functions of functions on the closed interval. This is the Banach fixed point theorem. So it seems that Banach, this stuff was in the water before Banach, but it seems that Banach was the first person to sort of champion this as a universal. I think you found these fixed point theorems in different parts of math, but he kind of just drew it together and sort of generalized the idea. And he probably didn't call it the Banach fixed point theorem. Unless
he was full of himself.
Yeah, it seems unlikely he called it. He probably, who knows, I don't know. I'm not.
Trump fixed point theorem.
It's gonna be more fixed than any other fixed point theorem. Yeah. Other fixed point theorems will be fixed points of our theorem. It's meta-fixed. I'm sorry, I had too much political news for too long. I was watching the differential geometry lectures from the summer just for somebody left a comment, so I happened to watch a little bit, and she was saying something about the Republican debate. I was like, what? And then I was like,
You made some comment about it.
oh man,
That was like the first one.
holy cow, like that the Republican debate was that long ago. The first one. We've been talking about this since last summer, early last summer. My goodness,
It's too long.
holy cow, why did we talk about this for so long? Oh. really annoying. I mean, I'm a political junkie, but even so, you need some time to heal. Let's see here. Let S denote a set of continuous functions. So he says let S denote the set of continuous functions. Okay, so it's not a continuous, it's the continuous set. It's not some subset of these. It's the whole thing. That lie within, oh yes it is. It's not this, it's not this. It's a subset of this, right? Oh, good grief. I'm trying to look at complex. What am I doing? So it's a subset of the continued functions. Which subset? It's functions that do what? That lie within distance alpha of a given function. Why not? So, in other words, you could think about the picture I had before. It would be like all functions that have a graph that's within the alpha band of y naught, you know. Well, okay, so he defines it carefully. All right. Suppose that G is an operator mapping of S into S. So G is a mapping from S into S. Remember, we had to have that into condition before. And such that G is a contraction on S. What do you mean by that? In the sense what? Meaning, there exists a K, which is what? Yeah, 0 possibly included, 1 not included, such that the norm of G of W minus, by the way, these square brackets are customary. People like to write square brackets for operators to remind the students that it's not a function, it's an operator, because it's taking in a function, so we use square brackets to denote it's an operator. But this all seems rather ad hoc to me, because operator is just a function of functions, so I don't know, what's a big deal? I don't know. Okay, fine, why not just, whatever, it's notation. K, norm, W minus Z. And that has to be true for all W and Z and S. So for all functions that are within alpha of the given initial iterate, let's say y naught, right? What's the punchline? Then the equation. Now this theorem is not quite as greedy as the one we read in Edwards, right? Like Edwards had always had some kind of tack-on thing about how close the iteration was, you know, term by term to the sequential limit. And I would wager there's also a result like that to be culled from a more finesse presentation of the argument. But anyway, there's an equation to the fixed point equation, y equals g of y, that has a unique solution. Has a unique solution defined by the limit of the iteration of, you know, yn plus 1 equal to g of yn, right? In other words, to be more, to complete the thought here, the sequence, in particular, yn converges uniformly to y such that g of y equals to y, right? I guess you could put a y star or something. Well, he puts an infinity here, which is kind of nice notation. Infinity for the limit function. Sure, why not? Right. So it converges uniformly to this solution for any choice of starting function y naught in S. Now, I don't know what that means. He's used, this last sentence will blow your mind. I would not advise thinking about this too much. What do you mean? But why not was used to define S? What does that mean? I think we could reinterpret that as if you begin this iteration with any other, say, y naught tilde in the set S, where y naught is something fixed, it's given at the start of all this. It's used to define S, right? But if you were to pick some other element of S and iterate from there, you would also find your way to this same stupid endpoint. All roads lead to y infinity, as long as they start in S. And that's the Banach fixed point theorem for operators. From this theorem, we will derive the existence and uniqueness of the initial value problem for first order ODEs. And that theorem is very, very close. I mean, that almost immediately leads you to like existence and uniqueness theorems for all of your favorite your favorite differential equations. I think it's worth going through the proof of this. Let's go through it. I was thinking I can graph three-dimensionally now. You know, because I can do this.
Yeah.
Oh man, I guess I gotta make a choice. Alright. So then I can do things like,
How would you draw a line?
how would you draw a line now?
Coming out of the board.
Bloop. Bloop. How would you draw a plane? Glad you asked. Right. And so forth. But the cool thing is you can actually go like, see, it just comes out like this. You know?
He like Dr. Wang in his Calculus 3 with all the props.
Yeah, it's like the corner board is the ultimate prop for 3D graphing. I worked myself into a corner and I liked it. Let's see here, no, I'm sorry. Usually it's the opposite. All right, so here we go, proof. So first of all, enough of this marker. This marker is stupid. Why am I writing with it? A nice juicy marker. All right. Maybe this one. Again, this is actually an outline of the proof of theorem 1, which is but I think that the outline is sufficient. He's like, first of all, the YNs are well defined. Let's see here, let's start out with that. YN is how do we define YN? YN is equal to what? G of what? YN minus 1. And to start with, G of Y naught equals to Y1. Sorry, I wrote it in the opposite order. So the fact that we're assuming G is into means that the iteration at least makes sense, because if it's into, it stays into, and into, and into, and into. All right, enough. The approximations converge uniformly to an element of S. All right, so he says that if we look at the norm y sub j plus 1 minus y sub j. He says you can show that that's less than or equal to k to the j times the norm of y1 minus y naught. Of course, that's a specific number, that last thing, right? Now, I'd like to just stop and try to prove that. I think it should be reminiscent of how we proved it for the other. Do we need the? Is that the one we need to do the? How's this go? So let's see if we can work through that. This would be what? This would be g of what?
yj.
Yeah. And we're given that G satisfies this contraction condition. So that's less than or equal to K. Norm of what? Of yj, right? Minus yj minus 1. Yeah. But then that's less than or equal to k times norm of g of yj minus 1 minus g of yj minus 2, which is less than or equal to k squared. This is equality, actually. Now this is, I'm using the contraction again. And so forth. So eventually we get to what?
To the j.
So this was
It's like j plus 1 minus j.
j plus 1 minus j, which is
j. There 1.
y1. And j.
j minus j.
So if you can follow the pattern, well, there you have it. I mean, that's exactly. Okay, so there's that, right? And then what? What's the next? What's the next thing here? So now we use this new idea about partial sum of the series, right? Maybe that's not a new idea. Maybe that's the geometric thing we did, geometric series step we did before somehow. Let's see here. So he's like, okay, so look at this. We've got yn is equal to the nth partial sum of what? Of the series. Oh, y naught plus, right? J equals 0 to infinity of the difference y sub j plus 1 and yj. I mean that's just kind of almost a tautology. I mean, you're like y0 plus y1 minus y0 plus y2 minus y1, and you know it's the only thing that remains here is yn. Right? If you stop at n, the nth partial sum. So what? He says from 9, which is this right here is what he calls 9. All right. He's like, from 9, we know that the norm of each term in this series is bounded by the constant. So this series, right? Like this converges, he says, because since if you look at it, y sub j minus yj, that would be the j plus 1 rather. That's the jth term in the series, right? And the norm of this, as we have up there, is less than or equal to k to the j times a number, y1 minus y naught, right? So he says, well, just call this thing mj, all right? It's a majorant. It's the jth majorant for this series. And, of course, the sum, j equals 0 to infinity of m sub j, well, that, we know what that does. I mean, that is actually just y minus y naught, right? y1 minus y naught. That's the a, quote unquote, divided by 1 minus k, right? A geometric series result. That's convergent, of course. And so this is a theorem that is not proved here, but he refers to it, which is that if you have, so you have this series of functions, right? And if you can prove that it is dominated by a numerical series, in this case the m sub j, that's the jth term, well, if the sum of that numerical series converges, it then follows that the given series of functions converges uniformly. And but the uniform convergence of this implies the uniform convergence of its nth partial sum. Yn is the nth partial sum, therefore this Yn uniformly converges to some function. It's a very nice argument. Now, obviously, the gap here for us is that we haven't proved the Weierstrass M test. But if you actually look in an analysis book, it's not actually that hard a thing to prove. It's relatively straightforward. It's not that bad. Like he mentions here, you can look in Principles of Mathematical Analysis by Rudin, 3rd edition, or if you like Advanced Calculus by Kaplan. Kaplan? Okay. And we're going to suppose that we're going to say Yn converges uniformly to y infinity, okay? Now he's going to show that y infinity is a fixed point. How do you do that? So let's see here. We have, of course, that the norm of g of y infinity minus g of yn is less than what? It's less than k times the norm of y infinity minus yn, because, well, g is a contraction. These are two functions in S. But then what? Well, we know yn goes to y infinity as n goes to infinity, so this goes to 0. Consequently, this goes to 0, right? Which means that g of yn goes to g of y infinity. Or you put norms around that if you want, I suppose. Come on. Where was I? And that's a uniform convergence because we just got that this goes to 0, which gives us the uniform convergence of this to that. But this is what? This is yn plus 1. And that's y infinity. That's y infinity. So this uniformly goes to what? Oh, well, we already know that. That
y plus 1, yes.
So this goes to g of that, which is, by the way, also by definition up here, or a result, whatever you want to say, infinity. So there you go, fixed point. And the proof of uniqueness is the same proof we gave the other day. If you feed two different fixed points to the contraction condition, you end up with a contradiction if we're actually different. I know, I think It's a neat proof. Now, so that brings us to Picard's existence and uniqueness theorem. Good, I still have time. I'll move it along now. I guess we don't need, we shouldn't need this proof anymore. I'm gonna get rid of it. Oh, did you get it all?
Yeah.
Okay. Theorem 3, again, we're following chapter 13 of Nagel, Saff, and Snider's 5th edition differential equations book. So you have f and partial f, partial y, continuous on a rectangle R. So what you got is you got yourself x and y such that a less than x less than b and c less than y less than d. What are we, animals? R is equal to a comma b Cartesian product with c comma d. Is that so hard to write? Can't engineers understand that? Put that in your book, man. Sorry. Contains a point. I mean, is it so hard? Isn't this nicer? I don't know. So suppose x naught y naught is an element of this rectangle. Then the initial value problem, which I wrote on the other board, all right, which is what? Let's see here. Y prime equals to f of, oh fine, y prime of x is equal to f of x comma y of x. And y of x naught equals to y naught. Has a unique solution. Right here. Has a unique solution on some interval x naught minus h, x naught plus h, where h is a positive number. Well, that's good. I was worried it was a complex number. Right, for some h greater than 0. Moreover, the Picard iterations converge uniformly on this closed interval to this solution. All right. All right, so what we have to do is we have to produce a operator which is a contraction. All right. So we can use the Banach fixed point theorem and to get this wonderful basic theorem of differential equations. Right. So let's see here. What's he do? I mean, we're trying to. Our proof is what? I mean, a proof. Our goal basically is to set up what? The S for the Banach fixed point theorem, which is what, you know, like g in the continuous functions on some interval such that what? Such that the norm of g minus y naught relative to that interval, of course, are less than or equal to alpha for appropriate choice of alpha, right?